What we will try to understand is a problem called attraction, and this attraction problem is related to the goal function that we are optimizing and what we are asking the algorithms to do. So we have taken some data from this Empire dataset, this 10,063. These are here, so 10,063 is here. So they are particles from an inflammasome, and this inflammasome has a couple of structures. So one is 10. It is a ring of 10 subunits, and another ring of 12 subunits. So we have taken the one with the subunit. So here we have the ring with 10, and we have also the ring with 12. We have it in a separate file, and here we have the structure of one of them. I don't know which one. This is the 12-fold disk. So we have taken the particles from the 12-fold symmetric ring, from the 10 symmetric ring, and we will analyze them in different ways. And this is the 10, I think, or the 12. This is the 12. Okay, so now let's say that we take the particles with ring 12 and the structure of ring 12, and we do a refinement. So we do a refinement and C1 refinement. So C1 refinement. So let's say that this particle is pseudo-symmetric, or that we don't know that it is symmetric. So we do a C1, and if everything goes fine, then we should get something that is 12-fold symmetric, and this is the case. And it is true that we have started with something with a reference that is 12-fold, and still the resolution is not too high, but well, yes, we recovered the right symmetry. But let's say that we do the same with this case was CryoSpark. We do the same with Reliant, and now what we get is well, the resolution here, the claimed resolution is 20 or 19 angstroms, and actually the true resolution is much higher. So not of this structure we have reconstructed, but of the original one deposited at EMDB. So let's do it with Reliant. Now the claimed resolution is 33 angstroms, and what we see is that there is an asymmetric reconstruction. So there is a gradient of illumination, and this is because in this C1 reconstruction we can analyze what is the angular distribution, and we see that the angular distribution, most of the particles have been placed in one of the axes. So we will see it now. These are 30,000 particles, and let me open this one. So here it is. So we have the two results. So we see that most of the particles have been placed in one of the directions. So in one of these axes here. So while the particles, if the thing is symmetric, but we don't know, we should expect that they are randomly distributed along the circle, just occupying all the possible equivalent positions. So and this makes sense from the point of view of the objective function. So in one of my papers, the one describing CL2D, we describe when you assign a particle to a class, you have to compare that particle to that class, and for that you will use a correlation or Euclidean distance or anything of the sort. And anything that is somehow related to Euclidean distance you will have two comparisons. So one is the signal itself, but also the background. So let's say that you start averaging. So this the in the 2D class or in the 3D reconstruction, you start averaging. You assign more particles in one direction, so that when you average in that direction, the background becomes smoother because you are averaging more. So when you compare the background of experimental image to this smoother background, you will have a lower contribution because the background doesn't change too much, and then this difference doesn't change too much either. So the variance of the comparison will be smaller, and then there is a kind of variance barrier that the signal has to overcome to be assigned to the correct position, to the correct orientation. So once a direction starts getting signal to noise ratio because the background is becoming smoother, then more and more particles will like that direction. And so here we see it in 3D. So in 3D, what we see is this asymmetry that everything is along one direction, and we see these elongations. So this makes sense from the point of view of the goal function optimization. And let's see another manifestation of this problem. So we ask, we have this ring, we have these so particles from the ring, we have the ring, and then we ask a classification algorithm to separate into three classes. So these three classes are separated by angular distribution. So you can see that the change between the classes is that they have different orientations, and from the point of view of signal processing, this is a valid separation. So those are three different subsets of signals, but it is not the classification that we would like to have from the biological point of view. So just pure signal processing cannot solve the biological problem. So we have to put a priori information somehow, or try to guide the optimization in such a way that it converges to the right way, to the right point. So let's say that now we take the 12-fold ring with the particles from the 10-fold ring. We join the sets so that we know that we have 5,000 particles that are 10-fold and 30,000 particles that are 12-fold. And but we don't know. You are at the beginning of your analysis, and then you run it. So yeah, just before we do that, let me see what we have here. So we put all together the particles, and this is the structure that we have. So it is an initial volume blindly constructed from the 12-fold. So it is not perfect, and there are some artifacts clearly. These rings are artifactual, but otherwise it has the right symmetry. Okay, so now we have mixed the 12 and 10-fold symmetry particles, and we ask CryoSpark to separate, to construct two maps. So it has constructed two maps. The sizes are almost right, and then it is better if we see this way. So one has the 12-fold symmetry, while the other one is the 10-fold symmetry. So the other one is the 10-fold symmetry. Not perfect, okay, and it is not perfectly aligned in plane, but yeah, sufficiently different as to start a refinement process. Okay, so now let's see what Reliant does in this case. And what Reliant does is it converges to something that doesn't have actually any signal in it. So we can see here that it has converged to something completely not this one. This is not what I want. I want this one. Okay, so we don't see any signal inside. So yeah, and it has claimed that you have a current resolution of 3.4 angstroms. So this message has appeared a few times. So never trust these Fourier shell correlation resolutions blindly, because they measure consistency of so if I make systematic mistakes and I compare these two structures with the same systematic mistakes, the systematic mistakes will correlate pretty well up to very high resolution. So this is not a particular criticism on Reliant or Cryospark. Cryospark is better than Reliant or the opposite, but simply algorithms, depending on the specific runs, they may converge to different points, and you have to pay attention to which point you have converged. And we have this problem of attraction. So once a direction starts getting signal to noise ratio, it attracts things around. And here is another example of the same idea, but now on a different setup. So here we don't have two classes, we have just one class. So it is the 10,061 of Empire. So this is beta galactosidase, it is here. So it is this beta galactosidase of Subramanian, and here we are. So we imported the coordinates, estimated the CDF, and yeah, so at some points we have classes. So let's look at the classes, and yeah, some of them look very good. At the end we don't have so good classes, so we take the particles coming from the good classes. So for doing that, you choose your classes and you create a new set of particles. So we have taken 40,000 particles, and we have constructed an initial volume. So this initial volume claims a resolution of 7.6 angstroms. Yeah, actually not this one, we can go to the symmetrized one. So the symmetrized map seems to be a little bit moved, so kind of blurry, but good enough. So this is beta galactosidase, and yeah, so you can start your processing from this point. Okay, so now we run Reliant auto-refine, and we have obtained a 3.2 angstrom resolution structure, and looks more or less okay. It has very fine details. Some of them look like beta sheets. So yeah, so we are happy, and this is one of the messages why I tell you, I gave you this at the beginning, this warning. Okay, but all these problems are fine, but this is not my problem, because I have reconstructed a map up to 3 angstrom resolution. I see a lot of small details. Okay, so here in this map we see some weird behavior here. So all these stripes coming out, they are weird, they shouldn't be there. So this is an indication of an artifact, and this indication of an artifact, let's try to classify. Maybe we are mixing particles in two different orientations. So we classify each one of the classes claim 3.6 angstrom, or so we look at the two structures, and the two structures look different. This is the central slice of the two. So the two structures look different, and now you may start constructing your biological story of these are two conformations of I don't know what, and in these conditions and so on. But still, both of them, they also have this kind of weird stuff around. So you see this weird stuff here and there. So okay, can we analyze it differently? So I have taken CryoSpark, and in CryoSpark we have the beta-galactosidase or the structure, but we don't see those weird stuff around. So okay, so let's see if we have a problem with the angles. So we align this map and these particles to this one, and then we compare the angles, and when we compare the angles, what we see is that the angles, so for about the half of the particles they agree, but there is a big set of particles where they don't agree. So now we separate those particles, so the ones that agree, the ones that disagree and rely on. So now we take the two, so these are the ones that agree, 17,000 or 18,000 particles, and we reconstruct. We have a very nice looking beta-galactosidase. We take the ones that they don't agree, so the 23 or 22,000 particles that they disagree, just a technical note how to do this. So you take one of the sets and you take the other one and you compute the difference between the two. So we compute the difference, we reconstruct, and this is what we get. So actually our reconstruction before was a mixture between so let's go to the same place. So it was a mixture between this set and this set, and this set has a lot of small details. This set also has a lot of small details. So that is why, even if you say I have a reconstruction up to 3 angstroms resolution, so that is not my problem, I can see a lot of small details, still you might have a heterogeneity or misaligned particles, and you are analyzing a result that is corrupted. And even if you apply 2D classification, 3D classification, you may not be able to separate the two structures. So the two structures here, we had these two structures intermixed, and you were not able to separate them by 3D classification. And this is an expected result, because let's say here some particles, let's say half of the particles are incorrectly aligned, the other half are correctly aligned. So when you randomly split at the beginning, each one of the two classes will have this mixture 50-50%. So if you let them evolve, the two structures are so similar that particles cannot decide to which of the two to go. So they don't separate, and the two initial classes, they stay where they are. So this is a local minimum of this goal function that we are optimizing. So attraction is really a problem. Attraction is simply a local minimum, and local minimum caused by gaining signal to noise ratio. The misplaced particles, they have gained a lot of signal to noise ratio. So we see the structure. The structure has a very clean background with a little bit of artifact here, so that is why we have recognized this problem. But there is a lot of signal in between. So there is a high signal to noise ratio, only that it is the incorrect signal. And there are ways to try to identify these misplaced things, but the only way is to compute with something else and making sure that that the parameters you are estimating are the correct ones. So with this we leave this project and see you in the next one.